Alright, we're going to be doing 10.1 sound and waves. So first thing I'm going to do is go through the equations you need for this section. The first one is F equals KX. In this case, F is the force a spring applies. K is the spring constant. Force is going to be measured in newtons. K is the spring constant. That's going to be measured in newtons per meter. And x is the displacement measured from the equilibrium point. That's measured in meters as well. So that's our first equation. A lot of times you'll see that with negative kx because it's a force to pull it back to the equilibrium point. I think it's easier when you're doing math problems to just keep it as positive. We're also going to have lowercase f equals 1 over t, and t equals 1 over lowercase f. Lowercase f is going to be frequency. That's going to be measured in hertz, which is the same thing as cycles per second. And then capital T is period, and that's how long it takes to complete one cycle. And that's going to be measured in seconds. Right. Next equation is V equals F lambda. And for this one, V is the speed of a wave, speed or velocity of a wave. And that's going to be measured in meters per second. F is still frequency, and lambda is going to be wavelength. That's going to be measured in meters. Oops, those are both shrinking there. Our last two equations are going to be, second to last equation is going to be the period of a pendulum. That's going to be the period of a pendulum equals 2 pi times the square root of L over G. T is the period, pi is the number pi, L is going to be the length of the pendulum, and G is going to be 9.8 meters per second squared for the acceleration due to gravity. And I'll shrink that one down a little bit. And our last equation is going to be the period of a mass in a spring. It's going to be equal to 2 pi times the square root of m over k. T is still the period, pi is still pi, m is the mass of the object at the end of the string in kilograms, and k is the spring constant still, and that's in newtons per meters. So I don't remember its spring constant, but it's up there at the top. Alright, so first problem. We have, number 1 says, how much displacement will a coil spring with a spring constant of 150 Newton meters achieve if it is stretched by an 80 Newton force? So we have our spring constant, K, is 150 Newton meters. Our force is equal to 80 newtons, and we are looking for x, how far it's displaced. So all we're going to use is F equals Kx. And we say 80 newtons equals 150 Newton meters. Let me erase that parentheses, that shouldn't be there. Times x. So when we solve that, 80 divided by 150 gives us x is 0.53 meters. So that's number 1. Number 2. It says an amusement park ride has a frequency of 0.068 hertz. What is the ride's period? So we have F equals 0.068 hertz, or cycles per second. We're looking for the period. That's just terrible writing. Period is what we're looking for here. So this one's pretty easy. It's just going to be period equals 1 over the frequency. So that equals 1 divided by, should be a z up there, 0.068 hertz. And we do that math, we should get period is going to be 14.7 seconds. And again, that would be how long it takes to complete one cycle. So if this is something like a Ferris wheel, it would take 14.7 seconds to go around in a circle once. So that's number 2. Number 3 says, if a mass undergoes simple harmonic motion with an amplitude of 50 centimeters, what is the total distance it travels in one cycle? So this is not really an equation, this is more of a conceptual one. So if we have a mass attached to an awesomely drawn spring, that's the equilibrium point where it starts off if there's no forces applied. It's going to go, make this red. So if it ends up out here, 50 centimeters, if that's the farthest away it gets, that's the amplitude, and that's what it says it is. So the amplitude is 50 centimeters, so that's the maximum distance that way it goes. It's also going to go 50 centimeters that way from the equilibrium position. So to figure out the total distance it travels through in one cycle, it's going to go 50 that way, 50 back, it's got to go 50 that way, and 50 back to get back where it started. So if we add all those up, it's going to be 200 centimeters to complete one cycle. I believe the answer on this one is wrong. It says 100, which is wrong. To complete one cycle, it has to go there, back for 100, there, and back for another 100, because it has to be going the same direction in order to have completed one whole cycle. Alright. Number 5 says a 4.57 meter long pendulum has a bob of mass 63 kilograms. Assume the acceleration due to gravity is 9.81 meters per second squared. How many full cycles does the pendulum swing in 1 second? So what we're looking for here is frequency. Frequency is cycles per second. So we're looking for how many cycles it completes in 1 second. So if we find the frequency, we'll have figured out the answer to this question. So frequency is cycles per second. So first we're going to find the period using the equation period equals 2 pi times the square root of length over gravity. And then we're going to do 1 over that to find frequency. Let's find the period. So period equals 2 pi times the square root of L over G. So that equals 2 pi. The square root of our length here is 4.57 meters over G, and it gives us G, so we'll use, gives us G as 9.81, so we'll use 9.81 instead of 9.8 meters per second squared. And so we do that, and when we do that math, we should get our period is 4.29 seconds. That's a 4, not a 9. I'll erase that. That's terrible. 4.29 seconds. Now we just need to do frequency equals 1 over the period. So do 1 over 4.29 seconds. When we do that math, we should get our frequency is 0.23 hertz, which is 0.23 cycles per second. So this pendulum, it does not complete a full cycle in 1 second. It completes 0.23 cycles in 1 second. Alright, number 6 is the last one we'll do together. Number 6 says, a mass in a spring vibrates in simple harmonic motion with an amplitude of 4.0 centimeters. If the mass of the object is 0.85 kilograms and the spring constant is 140 newtons, what is the frequency? I forgot to mention this in the last problem, that the mass didn't matter on that last problem on number 5. On number 6, the mass will matter, but the amplitude won't. So in this one, we're going to do the same thing again. We're looking for frequency. So we're going to use the equation period equals 2 pi times the square root of m over k to find the period, and then use that to find the frequency. So we have t equals 2 pi times the square root of m over k. So we get 2 pi times the square root. Our mass is 0.85 kilograms over our spring constant is 140 newtons per meter. And 2 pi times the square root of that is going to give us 0.49 seconds. So it's 0.49 seconds for this to complete one cycle. And to find the frequency, we say frequency equals 1 over the period. So frequency equals 1 over 0.49 seconds. And when we do that math, we get our frequency is 2.04 hertz. And that is the end.